So let's get started. Thank you so much for joining. And this is the Exploratory online seminar number 88. Today, I like to go cover the multivariate analysis. And I put the subtitle, How Great Do I Perform Without Others? I think that essentially the whole multivariate analysis trying to do is basically this. So I think if you're already familiar with it, it's great. But if you are not, I think yeah, I want you to kind of notice. Remember this subtitle. Okay. So today's agenda, I'm going to start with the correlation and what's the problem with the correlation and how we can address it. And obviously, that's where the multivariate analysis comes in. And then I'm going to use a linear regression as an example. And at the very end, I'm going to talk about the limitation and then, possible solution for that to address such limitation. Okay, so let's get started with a problem with correlation. But, before getting into the problem, I think correlation is actually a really powerful tool. What the correlation is the changes in one variable. When I say variable, by the way, is a columns. When you see the spreadsheet or whatever the table format data, it's the column. Okay, so changes in one variable correspond to changes in another variable with a certain regularity. And most of the time, like it can be some kind of like you can use like a formula to explain that regularity or rules or something like that. But anyway, more details on the correlation. I have just done that, like the seminar last week about the correlation. So you can go to our website, exploratory.io, and then go under the Learn menu. You see Training Seminar. Under that, there is a correlation, and you can find like a recorded seminar there as well. So I'm not going to go into the too much detail on the correlation, but I'm going to cover the very high level brief. So for example, when you have like data of the sales data, and then you also have the variable called time spent on website on each customers or something, and then like you can see like for example in this chart, like you can see like the more time the customers spend on your website, the more sales that they actually make, or the more products or more money they use, right? So why do we care about the correlation? It's actually an obvious reason, because if we can find the correlation, meaning like the relationship between, for example, these two, like sales and time spent on website, then we can use that relationship to be able to predict, right? Predict, like, okay, for example, this customer is spending like 20. Let's call it 20 minutes instead of 20 hours. So let's say 20 minutes. Then probably more likely like this person is going to spend like around the $4,000. Might not be the exact, but instead of saying like, oh, can be zero, can be 5,000, instead we can pinpoint around like $4,000. And this relationship is like numerical variables and numerical variable. Sales is a numeric, is like numbers, right? And time spent on website again, also the numbers or numerical variable. But it doesn't have to be numerical relationship. It can be categorical and then numerical. And then, to expand, it can be categorical and categorical as well. But in this here, like just for the sake of the simplicity, like I'm going to use that categorical with campaign, without campaign. You're maybe doing some kind of sending campaign email or something like that. And then the customers who received the campaign emails and the customers who didn't receive the campaign email. And then do we expect the different sales numbers for like monthly sales or something like that? This case, we have the higher sales for the with campaign customers. So therefore, we can say like, okay, if we do campaign, we can expect $5,000. This is like an average or mean. Okay, or at least we can say like the customers who receive the campaign emails tend to spend more dollars than the customers without campaign emails. Okay, so if we find this kind of relationship, that's actually really valuable information, right? To be able to explain what makes that difference. Also be able to predict what is going to happen. And possibly like you can control, in this case, for example, because of this, we should send the campaign emails so that we can expect more sales from the customers, right? So So there's a lot of good things with the correlation or being able to find or discover correlation. So in this seminar, like I'm going to use employee data. This is a kind of series I've been doing over the last, I don't know, 5-6 weeks, ranging from hypothesis tests and correlation, and then all the statistical stuff. But I always try to use the same data. So again, this seminar, I'm going to use the same data, employee data. Each row represents each employee. And then we have like 27 columns, meaning the 27 variables or employee attributes, such as age or monthly income or job roles and so on. Okay, and if we use this data, and then we can actually use the correlation mode of the exploratory to quickly discover and investigate the correlation. So let's take a look using the exploratory. So here, I already have imported the employee data here. Okay, and I'm going to hide the left-hand side sidebar. And then let's go start from the table view. So here we have each row is each employee and then all these employee attributes. Okay, and then what we get interested in today is this monthly income columns. Okay, so let's take a look at this, go to the summary view and then see. So if you open the exploratory, this is you would see under the summary view. And then like, where's the monthly income? Okay, here it goes. So this is like a monthly, how much this person and all these employee getting paid, right? Ranging from about $1,000 to about $20,000. There's a quite variation there. But what makes this difference? That's our interest. So you can go to the correlation by clicking this correlation button. And then usually like you start with something like this. So nothing has been selected. And then like you want to actually select the thing, select the variables that you're interested in. You can select either numerical or logical. So in this case, we are interested in this monthly income, which is a numerical variable. And what just happened is that it investigated or like it basically does the calculation around the correlation for every single column other than monthly income in this case. So for example, like job level monthly income, it actually calculate the monthly correlation efficient, which is here, the second one, correlation Pearson. And then the first one is the R squared, which is basically the square of the correlation Pearson values. And then the significance p-value, which is basically the result of the hypothesis test. Okay, so it's significant because p-value is 0.0, pretty small. And then correlation number is 0.9503, which is pretty high. R squared is 0.20. Again, it's pretty high. So you can find that quickly. Not only the job level, but it does that like, for every single column. Okay, so and then it's sorted by the R squared. R squared basically the indicator of the strength of correlation, ranging from 0 to 1. Closer to 1 is the strongest, stronger the correlated relationship is. Okay, and then so now here, what we have is like a job level, job role, total working years, age, and looks like these are correlated, right? And then by looking at these correlation numbers, okay. So as obviously, like for example, this here is the age. Okay, so this company, the older you get, then the more salary or more income you get. That's the kind of relationship we are seeing. It's not like strong correlation. It's not like a strong correlation coefficient is 1, but it's pretty relatively strong relationship is here. Okay, so obviously now we have a relationship between age and monthly income, and that's the thing that I think today's topic. So there is a correlation. And last week another seminar I talk about correlation stuff. And then one thing we need to be careful is that relationship is significant or not, statistically significant or not. And it says p-value is less than 0.0001, 0.01%. So it's highly unlikely to accept a null hypothesis. So this is a significant relationship. So we know that there's a relationship, and how strong the relationship, that's like this correlation number. And then again, it's like a relatively strong relationship is there. Okay, so age matters in this company. But there is one thing we need to be careful. That's the problem with the correlation. So here's a quote by Ralph Waldo Emerson, which is like American author. Shallow men believe in luck or in circumstance. Strong men believe in cause and effect. So I think this is a sort of basically the key, right? The problem with correlation, because correlation is no causation. I'm sure like you have heard about this phrase, and any like a statistical teachers will tell you. But what it is basically when you find a correlation, let's say like ice cream sold, number of ice cream sold, getting higher as the months goes by, like let's say May, June, July. But also number of the shark attacks also increases from May, June, July. Then when you look at these two, like, okay, maybe in order to sell more ice cream, we should have more sharks invited to the ocean and attack the people. Obviously, you don't think that. But is that this relationship? And based on the intuitive sense, you'd think like, oh, that's just a kind of coincidence, right? So that's actually right. But when I draw the picture, the relationship is kind of like this: shark attack, ice cream. So like either increase in ice cream sales and cause increase in shark attacks, or vice versa, increase in shark attacks, more shark come to the ocean and on beach, and then like maybe somehow like we can sell more ice cream. That sounds like more plausible than the other. But neither of that is actually true. It turned out it's actually the temperature is the one causing the number of the ice creams, so impacting on the number of the ice creams getting sold, and also number of shark attacks. And this kind of this kind of factor is called confounding. So the temperature was hidden, but we were actually looking at just ice cream sales and shark attack, and we concluded that maybe like I was the only one who concluded that there is a relationship here. And then that when I said relationship, I thought that could be more like a causal relationship. It's not just like happened to be this correlation. Okay, but it turned out the temperature is the one causing the more shark attacks and ice cream sales. Obviously, like the hotter the weather is, like more ice cream you can sell, but also the like people going to the beach, going to the water when the temperature increases, right? So like more chance for shark to attack. So temperature is that confounding factor. Okay, so this kind of stuff, I mean, if this is a shark attack and ice cream sales, and it's kind of obvious, but that happens a lot, pretty much everywhere when you look at the data. And surprisingly, like most of people actually don't even bother to investigate further. Instead, they stop. And when they found the correlation, and they conclude it right away. So that's the danger of that data-driven approach. Like if the more data you have, you think that you know something, by finding some relationship in there, but you gotta be careful what that relationship is and stuff. So in our data, let's take a look at the monthly income case again. So we found that age and monthly income have the relationship, right? So like the older the age is, the bigger the monthly income will be. And then, so it's that part. And not just age though, it's also like, job level, job role, total working years, and these are all correlated to monthly income. And then you go, maybe like we can conclude, hey, in these companies, actually the salaries, decided on the age, and then you can say all sorts of things. But we also know that job level and monthly income are related, right? So, okay, so that means we can create this kind of a diagram. So job level at the top and the right-hand side bottom is the age, left-hand side bottom is the monthly income. And then looks like age and monthly income is related, and job level and monthly income is related. Then the problem is when you remember that shark attack and ice cream, this is actually, we have this triangle relationship, maybe, right? So like if we have the relationship between the job level and the age, then that could be a little tricky. So let's try to find out. So here, right now, we have monthly income as a target variable. We can change it to any numerical stuff. So like I'm going to change it to job level. Okay. So if I change the job level, it will do it. It just did the same thing. It's trying to calculate all the relationship information between all the columns and the job level. So in this case, for example, job level and monthly income is obviously the strongest relationship among all these variables, but also look at the age. Age also has a relationship with job level, and the correlation is 0.50. Okay, and then it's significant. So that means, going back to this diagram, we can say that there's a relationship between job level and age. It's not like one-on-one relationship. It's not like if you know the age, you know the job level perfectly, but there is a certain, there's relatively strong correlation between these two. Okay, so here's the problem. We have the triangle relationship, and it may include this like a confounding factor. Okay, meaning job level could be the confounding factor. So then we might be just seeing the age and the monthly income as a result, right? So, so what that means, the job level changes, then that will impact on the monthly income. So job level is 1, 2, 3, 4, 5, and then obviously, like the higher the job level is, monthly income it will be higher. And then it turned out job level and the age have the relationship, the higher the job level is, and then the older the age is. So maybe like we're just looking at the result that both of them caused by job level. And it's kind of weird. I mean, like what, like if you go into that higher job level, and you're not going to get older. It just, so in this case, the English is kind of weird. But the point here is that higher the job level, then higher the age would be. And then it's not like this company is making the monthly income decision based on the age. It's just that more like a job level. And the job level can be decided by various reasons, right? So maybe like age actually doesn't matter. Or vice versa. Actually, age is the one who it matters. And in this company, the older you get, somehow automatically you get a higher job level, but also you get the highest income. So therefore, of course, like a job level is higher because this person is on older age, and then monthly income is also higher. And we are just looking at the job level and monthly income, and by creating a chart or whatever, this sounds like, it looks like there's a relationship, but no, like it's not like a direct relationship. It's not like a job level is the one causing the monthly income higher or lower. It's actually the age is the driving force, right? So what's happening here is, how can we know? What essentially we want to do is, can we know the effect of only job level or only age on the changes in monthly income? So basically, like it's sort of like independent effect of each variable. And that's why, like I said at the very beginning, as a subtitle of this seminar is, how great do I perform without others, without other people, right? So if we forget about all the stuff, without the job level effect, can age or does age still have any effect on the monthly income or vice versa? So what that means, so when you look at here is if there are two groups I picked from this employee data in this company. Okay, one is a 30 years old group, and the other one is 31 years old group. So the difference is 1 year old. And it doesn't have to be 1 year, it could be like 5, 10 years, whatever. But the two groups, the difference is the age difference. And then I calculated the mean income, monthly income, and it turned out 8,000 and 10,000. Oh my gosh, that's 1 year and $2,000 difference. Okay, so this sounds like an older group. If you're older, you get more. But then when you look at farther or deeper, and I found that actually the older group have more higher job level like 2 or 3, those are like orange and purple. So when you look at something like this, and obviously the reason the group on the right is getting paid higher is not purely coming from the 1 year old or age difference, probably like a job level, or we don't know, but both of them can play some role in terms of increasing the income, right? So what can we do about this? Then obviously, like how, one solution is here, simple. Let's just get only job level 1 folks. So both group, I remove job level 2 or 3 people, and then I just compare only the job level. And then when you have like age difference, do we still see the difference in income? And we can do the same thing for the job level 2, job level 3 as well, right? And then if we see the 31 years old group has a higher income, then we can conclude, oh, okay, age actually plays some role, right? And maybe like the difference might become very small or very large, who knows? But nonetheless, basically what I have done is by sort of like creating an equal condition between these two groups, except the age, then we can see the difference in the income or mean income. And then if we see the difference, then we can say, oh, age is the one. If we don't see the difference, then, oh, you know what? It's not the age, actually, maybe the job level or something else. So what we did is we can hold one of the two variables constant, meaning like values stay the same, and then see if we still see any change in the monthly income. So what that means? So for example, in this triangle relationship, we can keep the job level constant, like just one, job level 1, and they don't move it, or like just filter out only those people. And then we observe like, okay, like age 10, 11, or 11, 12, and 12, 13, and do we see any impact on any difference in the monthly income? We can do that the other way around. It might be age is the one, right? So in that case, we can just keep the age constant and only allow job level to move. Then we see any change or not in the monthly income. So that's the kind of thing we can do with multivariate analysis. And multivariate analysis is just kind of like umbrella word. It's really statistical running model, analysis by using the statistical running model. So it can be linear regression, logistic regression, and so on. And Exploratory is a bunch of analytics. I have this diagram, depend what you want to do, like you want to use different type of algorithms or analytics. I'm not going to go into all the detail, but here is an important thing. So here, based on like what you want to do, this is more like a building a prediction model, and left-hand side bottom is more like if we want to predict numerical values, in this case, like income or sales or something like that. Right-hand side to and above or bottom, these are basically same thing with a slight difference, but either ways, you want to predict a categorical, like true or false, or like ABC or something like that. And at the bottom, center bottom is a survival rate. That's a survival analysis or cohort analysis and stuff. Okay, but regardless of the difference, you see the color difference. So green is a statistical running, which means is that there is a formula. It's like a new mathematical formula is the model that builds up. That is actually the prediction model. As opposed to that, the orange is the machine learning. Okay, that means in particular in this case, is that there's a rule base. So it's imagine, just think of it as more like a bunch of if else. Like if something happen, if this condition matches, and then value will be this, and if that otherwise value will be that. And then you have the bunch of those rules, and depends on which algorithm you use. Okay, but you can do this multivariate analysis only with statistical learning model. I mean, this, over the last few years or whatever, and then people try to do this, multivariate analysis by using machine learning model, and they've been researching all that stuff. But so far, basically, if you want to do multivariate analysis, like you want to go with the statistical learning model. That's because it turned out the formula that that is the foundation of this statistical learning prediction model is the reason we can interpret the whatever the model is returning in a sense that what we expect whatever the running model to address, which means like if you remember, like we want to keep one variable constant, or maybe it doesn't have to be one, but the other variable is constant, and then allow only one variable to change, and what would be the difference? And the statistical running model can answer the question thanks to the fact that it uses mathematical formula. Okay, so today I'm not going to go all of them. I'm going to go just focus on the linear regression model. Okay, so let's go into the linear regression basics, but I have done the linear regression model seminar in the past. Again, go to the exploratory.io, and then under that learn, you go to the training seminar, then you go to the online seminar page, and then you click at the link at the bottom of that page, and you can get a series of the seminars. But online seminar number 14, I have done the linear regression seminar. So you can see more detail on there, it's 60 minutes of the detail. Today, I don't have that time, so like I'm gonna go very basic stuff, okay? So, but still, like I wanna introduce key elements to it. So here in Exploratory, there are two ways to build a linear regression model. One is going to the analytics and then select a linear regression model and then assign required variables. Or the simplest way, because we are in a correlation mode already, you can create a linear regression model from the column header menu, okay, as long as you are in a correlation mode. And then when you click, you find a create linear regression. So you want to click on that. What it does is basically move to analytics and then create a new tab and select a linear regression model and select job level as a target variable, and then age as a predictor variable. That's it. So you could create it by going to the analytics view manually from scratch as well. But anyways, I'm lazy, so like I'm good with this. So now like what we are looking at here is that this blue line is actually the model. It's kind of weird, but model is basically the formula, but the formula returned the values and then we just connected those dots. So this is the model, and then so as age increase, and then oops, I have actually job level as a target variable. I am so like airheaded today. Let me go just back to summary. We don't care about like prediction of job level. We care about the monthly income. So I totally forgot like we switch the target variable to job level. Instead, what we want to do is like this monthly income. So we got to be careful on that one. And then age. We are interested in the relationship between monthly income and age. So from again, column header menu and create linear regression. I could just change the target variable under the analytics view, but I'm going to just restart from here. Okay. So create the linear regression, and then so all it does is basically just change here instead of job level and the monthly income. Again, I could have just switched this one. But anyway, so as age increase and then the monthly income increase, and that's what we are seeing here. The gray line is actual values. What that means is like it's created like 20 buckets or 20 sort of like each, what do you call it, like divided by with an equal width. So like, for example, like 20 to 25, 25 to 30 or something like that. And then within that area, within that length, the bunch of employee, so that we calculate the mean of the monthly income. And then you connect those mean incomes for each all the sections. That's actually the gray line, and with the confidence interval, 95% confidence interval. And then this blue line again is a model. Okay, so let me explain what this thing is just quickly. So linear regression model is really essentially is that, for example, here we have the age as x-axis and the monthly income as the y-axis, and we have like 5 employees or 5 data points. And the linear regression model is to try to draw the line in the middle to make sure that distance between the line and all the data points to be minimum. Okay. And that's what that linear regression model is. When you go to the coefficient table, you can see something called parameters or coefficient. What this coefficient means is that by using that, you can create this formula. So monthly income equal 256 multiply age minus 2,970. This is minus, but it, when you see the linear regression model formula, you typically see as a plus. Always you want a plus. However, when you look at here in the coefficient, you see like intercept. That's that green one. It says minus 2,970. That's why like here's a minus. Okay. So what this means is that first of all, the 256 is a slope of that line, this straight line. Okay. And what that means is that as the age increase, 1 year old, one value increase in the age in this from 31 to 32, for example, then the income would increase $256. Then another one is the minus 2,970. This is called y-intercept. That means when the age is 0, where would be what would be the monthly income? So that's minus 2,970. So if the baby joined this company, then they're gonna, the parents have to pay $2,970. That's kind of just a theoretical thing. I don't think that's even anything close to correct. But what this formula means is the minus 2,970. That's the point that age is 0. Okay. So again, going back to that formula of the linear regression model. So these 256 and minus 2,970, these are called parameters. In this case, a coefficient. But linear regression model is what really doing is that to find the most appropriate parameters based on the data, based on the relationship in the data between the age and monthly income. Okay, and then that really, again, the target is to make the minimum between the line and all the data points. So when we have this coefficient, and here is a key thing. So what it's saying is that like 1 year increase in the age, you get $256 salary or income increase. Does $256 significant, or like does it even matter? So that's something that you can go to coefficient tab. You don't have to. In this chart, you can see, for example, let me just go to what we are looking at is here, coefficient table. And then you can see like, okay, what's the p-value? And p-value is 6.66, but at the end, it said E minus 93. That means the power to 10 power to the 96. So basically, you said 0.000. You said 93 times, and then 6. So it's very small numbers. Okay, if it's plus, then it's going to be like 10 power to 10 to the power of 93 or something. But this one is a 0.1, so like minus or 10 minus power to the minus 93. So it's very, very small numbers. So that means you already know like, oh, this is significant. But I'm not a really p-value guy. Like I'm more a confidence interval guy. So like, I can see here the confidence interval low to high, the 233 to 279, and doesn't include 0. So like I already know this is significant. However, it's always nice to see visualize. So here, not only the p-value is actually driving the color, so if it's not significant, you would see gray color, but to me is this error bar. So you see the coefficient $256, but however, like I'm also seeing this range. The range represents that confidence interval. And if this interval contains 0, then that means like it could be 0. That means coefficient could be 0. That means the line slope could be 0, like flat. So that means doesn't matter. Any age you go, left or right, it's always the same income. That means there is no relationship, right? But this one doesn't include 0, so it's not gonna be most likely not 0. If there's a 5% chance can be 0, but it's most likely not. So therefore it's significant, right? So long story short, here we know that age has that relationship. And we don't have to actually build this linear regression model to say, hey, there's a relationship between monthly income and age, and that's significant, because we already know that. We already know that same information under the correlation mode, under the summary view. But you remember, we might have that confounding factor, right? So this correlation might be kind of like a pseudo correlation. It may be fake correlation, right? So that's where the multivariate analysis comes in. Why that kind of stuff, I already explained it, but I want to just focus on why this linear regression will help us address that problem. So far, we have done something called simple linear regression, meaning there's one predictive variable, in this case, the age. Okay, so the formula is monthly income equal to 256 multiply age minus 2,970. Right. So what that means is that, like, in order to interpret that, is 1 year increase in age would expect $256 increase in monthly income. Okay. So this is simple linear regression. And then now we go to multiple linear regression. That's where the multivariate analysis Sophia. Now, like, as you notice, though, there is extra predictor variable. It doesn't have to be 2, it can be 3, 4, 5, whatever. But in this case, I'm just trying to make it simple. But what this means is that, like, let's say, like, I just added the job level as a second variable. So now we have the age and job level 2 predictor variable. Okay, and then so now it turned out that age coefficient is 256 and job level coefficient 600. If that's the case, then we can interpret that 256, the coefficient or slope of the age, we can interpret this way. So 1 year increase of age would expect $256 increase in monthly income. This part, no change. It's basically the same thing as a simple linear regression. But next phrase is the key. If we hold job level constant, that means if job level doesn't change, then we would expect age, 1 year increase in age, we would expect $256 increase in monthly income. Okay, so that means if the job level is just 1, and then, like, you know, all the 1 people, okay, maybe like 100 people is all job level 1, and then among these, then there's an age difference, and then that difference of the 1 year old would change, you would see the $256 difference. Okay, so this one is like, I have, again, like only 2 predictor variable. What if, like, we have more, let's say the job level and then maybe job role, or maybe like a gender or something else, then we can still understand very similar ways that 1 year increase of age would expect $256 increase in monthly income if we hold, instead of just saying job level, all the other variables constant. So it's pretty convenient because mathematically, like, this formula can be understood. I mean, like, what is this $256 means? That's what it really means. You can actually try, like, you know, changing the different values, the job level 1, 2, 3 or something, or age, you know, 1, 2, 3, and then, like, you can see, like, what $256 really mean. Okay, but anyway, so now that we can use this multiple regression model, then we can actually go back to Exploratory and try it. So here, the predictor variable, right now, we have only age. You can click on this, and then we want to bring in this job level. Okay, so now we have age and job level as the predictor variable, and then click OK, and then run bottom. And then we have now 2 predictor variables. And then I'm in a coefficient, this chart. Let's go back to a coefficient table. You see here, like, we have now, like, age and job level 2 variables plus intercept. Okay, and then here, notice that, like, age is now like $9.45, $9.45. Like, if you get 1 year older, hey, congratulations, happy birthday, I give you $10 increase, and then you'll be upset. Well, you know, at least you get some increase, so that's actually maybe nice. But nonetheless, so this is what is the formula now. It used to be $256, now it's $9.45 for the age. And that is probably because job level is the one who's actually making the monthly income higher or lower. So the effect from the age got a lot shrink down. Okay, from 256 to $9.45, $9 basically. Okay, so now here's a question. this $9 matters? Is that a marginal difference, or it's still a significant difference? And then when you look at here is that when you look at the p-value, it's 0.05. And then, it depends on how you, what's your criteria. But, typically like 5%, greater than 5%, less than 5%, that's kind of threshold. So that means that greater than 5%, so probably it's not significant. Look at the confidence interval. I'm not reading the number guys, I'm more like a visual guy. So let's go to coefficient chart. And then look at the age, right-hand side. It's now the color is gray because of p-value, but also when you look at here, what's happening to the coefficient, this one looks like only the dot, but when you zoom in like this, and you can see this confidence interval actually contains the zero, because the low side of confidence interval is minus 0.07, like a negative. Okay, so that means we can't refute that there's a chance that the coefficient is zero. So therefore, might not be any relationship between age and the monthly income if the job level stays the same. So among all the job level 1 or job level 2, among same job level group, then monthly income might change, but that might be more like kind of random change, a random difference. Okay. But how about the job level? Well, job level is way high than the zero. So here is coefficient $4,000. So you get one level increase in job level, you'd expect $4,000 income increase, even when that same age people, only only the people are 40 years old or 41 years old. If we set the age as a condition the same, but you still expect 4,000 difference if the job level is difference in one level. Okay, and if this is kind of like confusing, it's like what is the coefficient, what is the one value difference and stuff, and you can always go to this predictive effect tab, and this is more like kind of visually explaining basically the same thing I was trying to explain. Okay, so to start with the age. So like no matter how old you get, the data itself is showing income increases, but without the effect of the job level, what would be the difference? That's what this blue line is showing. Okay, excluding the job level impact or effect, then this is the difference that this model or this data is telling us. And then so the slope is $9 or 9.45, and then that obviously it's almost like a flat, and like if like for example, I mean, like if you know this information ahead, then like you don't expect that, like your salary is going to be, increase after like 40 years or, working, right? So it's like it's like, what's the difference? I mean, $9, of course, like every year, $9, but so what, So, but anyway, so, but as opposed to that, like job level is, slope is pretty, accelerated or higher. And then even without the effect of the age, you still have a lot of effect on the monthly income. So we can say like, okay, in this case, what's happening is here, job level has a relationship with monthly income, but working years not. If we consider the effect of the other variable. So job level has an effect on the monthly income if we keep the working years constant. But we can't say the same thing for work. What's the working years? This is the age, sorry about that. Here, so we can't say the same thing for age, because if we keep the job level constant, then we allow age to increase or even decrease or whatever, the monthly income is not going to change. I mean, it might change a little bit, but that is very marginal, and it probably just a random difference. Okay, But wait. How about the other variables? It's not just a job level. Maybe even job level might be impacted by something else, right? So go back to here. We saw like job level, job role, total working years. Total working years is similar to age, but this is like how many years you work at this company. So if you join this company as the age of, let's say, like 40 years old, that means you're 50 years old, but your working years is still like 10 years. So it's a similar information, but it's actually can be very different. Okay, but anyway, total working hours and age, we have 4 variables have relatively strong relationship with monthly income. So how about the others? We already investigated job level and age, but job role and total working years. So let's take a look at that. Okay. So, but before going there, actually, there's one more tab here. It says importance. This is called variable importance. And when you look at here, it's obvious. It's like this is basically gives you the idea like which variables are important in order to predict the monthly income or to be able to explain the monthly income. And this model is basically using only job level. This height difference, basically age is almost like 0, and then job level is big. And that difference is, this y-axis is just a relative importance. So this 40 million doesn't mean the $40 million at all. It's just compared to age and the job level, and it's just relative numbers. So don't care about this like a y-axis scale, but it's more like care about the difference between these two. Okay, so go back to summary view, and then again, I want to make sure the target variable is monthly income. And then here, job level to age, I'm use a shift key. You can use shift or control key or command key. Then I'm going to rebuild the linear regression model. Again, I don't have to, like, basically what this is going to do is, like, if I select the linear regression, it's going to build the model. But typically, you don't come back to summary view again, right? So usually, like, you're already here, why don't you just extend this model? Let's do that. So click on the predictor variable, and then job role. And then what's the other? Total working years here. Okay. So we have selected 4 variables. Okay. And then click OK, and then run bottom. And then here, let's go step by step, even though, probably like what you need is a prediction important stuff, but I'm going to start with the coefficient table. And then here you can see the coefficient. And the reason we have a bunch of variables for the job role is because job role is a categorical variable. The categorical variable will create sort of like a variable for each category or categorical value, except the base level. If you're interested in what the hell I'm talking about, you want to take a look at the linear regression seminar. I talk about that more detail. But anyway, so here, and then like the next one you want to go is like here, it's coefficient. That this stuff basically visualize that table number, character information. So anyway, here, same thing, age is not significant, but how about the job level? Okay, job level is still significant. And I think the coefficient number got a little bit smaller. I thought it was like a 4,000 or something like that, but now it's 2,700. That's because this 2,768 can be interpreted as when all the other variables are the same. Okay, so job role is the same, and age is the same, and where the total working years is the same. We collected those same people on those 3 variables. Then the job level is different than what would be the change in the monthly income. And then it's saying $2,768. How about the total working years? Like I said, total working years is kind of similar to age, but slightly different because people join the company at a different age. This one, it says $46. $46 is a small difference, but still significant. Okay, because the p-value is pretty small, or confidence interval doesn't include or doesn't contain 0. Okay, so from here we can say, okay, job role, obviously job role, not all of the job role, but most of the job role, and then age and then job level. These, no, sorry, age, working years, job level, and then job role. These three are significant. Okay, and then but the age is not. And when you go to the importance, this is where like you appreciate the importance because you can see that relationship right away. So basically, obviously, age probably doesn't matter. Total working years matters. I mean, significant. That's why it's blue. But at the end of the day, it's a very minor difference that would make. But job level is obviously the number one job role. And you can argue like, hey, usually any company job level and the income are super correlated because probably that's how the income decided. So yes, probably. So that's kind of a little bit of weird, but anyway, nonetheless, I'm just kind of trying to focus on what the linear regression can do. Here, and the job role also plays a role. So what that means, again, go to the prediction tab, and you can see what that actually that relationship would be. So job level, like we saw in the previous one, like we had only job level and age. Then at that time, like this blue line, which is the predicted values, and the actual gray line was very along, like going along together. It's almost like overlapping or something. But there's some difference here. Right. So what's happening? It's not like it's not going middle of the gray line. That's because when job role, total working years, age probably doesn't matter, but the job role, total working years, those things are same and constant. Then what happened when the job role increase? And it turned out like after 3, like it's not like these folks, job level 3 people and 5 people. Probably these guys decided the monthly income decided because their manager or research director, these two groups have higher monthly income compared to other group, or maybe total working years is slightly higher, and whatever that could be, and that's coming from other than job level. So that's why there's a line is not called aligned closely after a certain point. Same thing can be said for the job role. If I had only job role for the predictor variable, then it's going to be like a matching. This blue and the gray will be matching. Basically, like only regression model can do is return the average as a prediction value. But there's a difference. And that difference is coming from the job level or total working years. So this is actually great because now like we can answer the question of like what happened. Like it's the same job level, same total working years, and then this guy's manager, and then what would be the change in monthly income? Well, compared to other group, then this is and how much manager would make. Okay, so we have now like we get this information, and then we can answer the questions very important to address the confounding factor. But there's a limitation, as obviously, like you might say, wait, how about the other confounding factor? Okay, the job level, job role, those are significant, have a relationship with the monthly income, but how about others? And in this data, or even like other, that not captured in this data has only 27 columns. And then what happened like after, other factors, maybe how many times you, went out with your, your boss, or you talk with your boss, or, like how about the writing skill, or like, other factors. So that's kind of stuff you can't answer by even using the multivariate. Multivariate can help you only all the variables are captured. Okay, as a data, and you have that data. So otherwise, what you do is like an A/B test. If you are familiar with that, how the web company or tech company do, or if we are more like a science oriented, then like RCT, randomized control trial. And what it does is that like using the A/B test, basically the same thing, but using the A/B test as an example, let's say like you argue like, hey, like we should change the button on the website color to blue or different color so that we can increase the the chance of the signups, right? Like clicking the sign up or something. Then you, instead of keep arguing about it or just looking at the data that you already have, instead you create two versions. One is the current one, and the next one is a new one. Okay, so like A and B. And then you assign, the people come to your website randomly to go into the original page or test page. Okay. And at this point, though, if you don't select this group randomly, instead, like somehow, like you go, like a certain user, like mobile user and a PC user or something like that, then you might end up like there's a difference between these two groups. Then again, like even though you're doing the A/B test, but you have basically like included the confounding as a design. So instead, you want to randomly split so that make sure the both group not going to be exact the same because one person can can go to only one page, but as a group, they're most likely two groups are kind of similar as long as you randomly split. Then have these groups going to that page A or page B, and then monitor that difference. And if it's A perform better, then you can conclude that A is better, and otherwise B is better, and so on. But this difference, the key thing is this difference between A and B must be coming from purely the change button color. Because again, these two groups, all the conditions are the same. So all the conditions are the same, but only the difference they see is the color of the button. You can't have like the different copy text, images, or something like that, exact the same, except the button. And also the customer or the user attribute is the same. Then this change must be coming from the button. The same thing for the RCT when you run RCT for maybe like testing the drug or medicine or something like that. The same thing. So these are the things that you can actually use because at the end of the day, what we are trying to find is a causal relationship. If you do X and then you expect Y, right? So to do, you gotta do like RCT or AB, but even without that, like at least when you're building a hypothesis or like if you're analyzing it, because it's not like everybody can do like A/B test and RCT, right? So the first step you want to do is that you have the data, you want to find, discover, and investigate if that is there's a correlation and the correlation is significant or not. But the next step is to make sure you do the multivariate analysis and then at least just kind of clean up or test your hypothesis by adding other variables to be able to see the kind of low-hanging fruits. And then in the real world, that if it's possible, you want to do the testing when you make such action. Okay. Okay, so that's it for today. It's almost like 1 o'clock now. So at the end, I like to introduce two things. One is that within a seminar like I introduced, but you go to the Exploratory.io, then you can find the training seminar page. Under that, you find like online seminar, you click it, and then you can find all the past recording, but also future seminar schedule. And also, if you Exploratory users, I highly recommend go to the Learn and then go to how to tutorials or how to video. We publish bunch of notes on the video on how to do certain things with Exploratory. So take a look. Okay. With that, if you have any questions or feedback, please send me the email at kan@exploratory.io. Otherwise, please follow us at Exploratory Data on Twitter. We announce this type of seminar or events, but also we publish a lot of tips on how to use and useful information there as well. Okay. With that, thank you so much for joining. Today's topic was the multivariate analysis with Exploratory.